Hey everybody, welcome back to another Chem Complete episode. And in today's episode, we are going to be tackling yet another unknown structure using organic spectroscopy. So if you've been following along, you'll know how to do this. If you have any questions about the steps we're taking as we solve one of these types of puzzles, then I would encourage you to check the link below in the description, because I will link to the online course that we have as usual for the full and entire free online course on YouTube as to how to solve each of these problems. So as usual, we'll get started with our degrees of unsaturation. So the formula here is C4H8O. So to calculate degrees of unsaturation, it would be 2 times the number of carbons, which is 4, plus 2. The oxygens are ignored, so we don't need to put anything for that. And then it would be minus the number of hydrogens, which would be 8. And then that gets divided by 2. So if you take a moment and you calculate that, you should get 2 divided by 2, which is equal to 1 degree of unsaturation. So the only thing that we could have here is a ring or a double bond. Now, if we take a look, it's 4 carbons because of C4. So that most likely means that we have a double bond. It's not impossible to have a 4-membered ring, but 5- and 6-membered rings are far more common. So I would propose we have a double bond, and given that we have an oxygen, there's a potential that we might have a carbonyl, but that's jumping the gun a little bit right now. We want to get some other evidence to support that first. So as we move along here, the next thing that we would take a look at is the mass spec. So the mass spec shows that we have M plus peak at 72. So this has a molecular weight of 72 grams per mole. And when we take a look at this, there's a couple of other important peaks here. There's one at 29, there's one at 43, and there's one at 57. Now these numbers are very familiar. It's a type of pattern that occurs when you usually have some sort of a propyl or butyl chain. So what I'm going to do is I'm going to pull up the guide real quick. So if you want a copy of this guide, you can go over to chemcomplete.com and pick one up for a couple dollars. It helps to support the channel and the free training I offer you guys on YouTube. Again, link will be down in the description. All right, so in Appendix A of the guide, we have the common ion fragment table. And if you take a look at 29, we have an ethyl group. Okay, you could also have an aldehyde, and we did say there might be a C double bond O, but you have ethyl. And then if you move down to 43, which is the next peak, we have propyl. And then if you move on to 57, for the next peak, we have butyl. So you also have an ethyl ketone as a possibility here. So you could have a C double bond O with an ethyl group on one side of it. So it's probably going to be likely that we have a butyl chain of some sort, because we only have 4 carbons. So remember, it's meth, and then F, and then prop, and then but. So 4 carbons would be butyl, and these peaks are certainly lining up to give the idea of a 4-member chain with probably a carbonyl. It might be an aldehyde, it might be a ketone. So we would have to look at the IR and the NMR in order to confirm that. All right, so what we can kind of predict is that we most likely have some sort of a 4-membered chain, so some sort of a butyl, and then somewhere in there we probably have one of the carbons is going to be double bonded to an oxygen. But let's confirm that by going through and looking at the other specs. So moving on to IR, which is our normal pattern, we come over to IR. We can see that there is nothing that is sort of north of the 3000 inverted centimeter or wave number region. So that means we certainly don't have any type of aromatic, but more than that, because we know we don't have aromatic from the degrees of unsaturation, you need at least 4. We did say there's the potential for a double bond, so we don't have any type of carbon-carbon double bonds that would have a CH stretch, because that would belong north of the 3000 region, and we don't see that there. Now what we do see is at 1718, that wave number shows a very strong peak, and that's important because that would be right around where a carbonyl should be. And 1718 probably is going to either be, again, an aldehyde or a ketone. So if you go and you look at the vibrational frequencies that show up in that region, that's right around the aldehyde or ketone region. So again, this evidence coupled with the mass spec and the degrees of unsaturation, we're really starting to support the idea of a carbonyl with a four-membered chain, an open chain, not a ring. So what we want to do then, since there's no other real evidence hitting us in the face here with the IR, is move on to the NMRs. So we'll start with the carbon-13. Now, if you've seen some of the past examples, we have a depth carbon-13. In this case, we don't have a depth provided. The only one is the proton decoupled, or your regular C13 NMR. But we could still gather some information here. All right. Ignore this little blip. That's your solvent. When you have this, we can see that there's 4 peaks. So you've got 1, 2, 3, and then the 4th one is hiding out way down here. All right. Now, there's a couple of important things here. The first one is that we have 4 unique carbons. And because of that, we know, since the molecular formula has 4 carbons, every single carbon is unique. There's not going to be any type of symmetry in this molecule. All right, now when you are this far downfield, so this one right here is around, I'm going to call it 210 ppm. The only thing that really shows up that far downfield on the carbon-13 is a ketone. So we can pretty well confirm at this point that we're dealing with a ketone functional group within the butyl chain that we're suggesting. An aldehyde, it could be in that region, but it tends to hang out a little bit more towards like the 190, 200 area. So a ketone is more probable. We can confirm this by proton NMR next, because if it was an aldehyde, that aldehydic proton would show up around 9 ppm on the proton NMR. All right, so now if we go upfield to these smaller ppm numbers here, the first one here is around roughly 8 ppm. Okay, anything that's pretty much below 10 ppm is almost always guaranteed to be a methyl group. So this is going to be a CH3, likely one of the 2 terminals. It's probably the one further away from the ketone just because it's further upfield. There's no de-shielding effects going on here. Right, and then we've got these 2 here. So if we have a butyl chain, right, and we're going to suggest that we have a ketone, that means that it doesn't matter where we internally put the ketone. These are the same structure here. So we have a methyl that's going to be on one side of a ketone. Then we have an ethyl group on the other side, right? So one of these is a CH2, and the other one would be for the other CH3, the one that's probably closer to the carbonyl group here. Now keep in mind, this is also supported because if we have an ethyl and a ketone portion, an ethyl ketone, when we were looking at the mass spec, 57 was an option for an ethyl ketone. So this fragment, it could be a butyl, but it can also be an ethyl ketone fragment, just like that. So this seems to support what the mass spec is saying, and that's good. Anytime that we have specs that are sort of building on one another, one supporting the next, that's what we want to see. All right, so we've got these others here. Another one, these I'd say is maybe roughly about 29 and 35. So this is probably going to be the methyl on the other side of the ketone. So this right here, as well as the CH2 group. All right, now let's give the final confirmation with the proton NMR here. Okay, so for the proton NMR, we have 3 peaks. So that confirms we don't have anything right here. This is where we would have seen the aldehyde proton. So if it was an aldehyde, we would have expected to see something here. That's not occurring, so we can definitely put sort of the nail in the coffin in terms of the ketone, and we know that that's what we have. So if we take a look here, we do indeed have 2 CH3s and a CH2. We just want to make sure that the splitting pattern matches up with what we were expecting. So if I were to draw this out, let's say we have methyl, and then we've got carbonyl, a CH2, and a CH3, right? So the CH3 that's furthest from the carbonyl, because the carbonyl is going to have de-shielding effects, is the one that would be the most upfield. So we're referring to this peak right here, okay? That would be associated with this CH3 right here. So I'm going to say that's about a 0.9 ppm, right? And if we take a look at this, this has a neighbor with 2 protons, so the n+1 rule would say we should see 3 peaks. And if you were to zoom up on this, you would indeed see that there are 3 peaks here. So this is a triplet, and that confirms the CH3 that would be next to a CH2. So then if we go to the CH2, which is this one right here, okay, the one that integrates to 2 over here is what we'd be looking at. And if you expand that, that comes out to a quartet. There's 4 of them. Well, that makes sense because the carbonyl has no protons, but the neighboring methyl group has 3. So 3 plus 1 is 4. That's the n+1 rule. And that quartet is going to show up right there. And that is, we'd say about 2.3 ppm. Okay, so you can see where this is going. The carbonyl, we have confirmation through other spec, but that's not going to show up on the proton NMR. And then finally, we have this last methyl group. This methyl group should show up as a singlet, and it should be further downfield than the other methyl group because it's closer to the carbonyl. And so indeed, we see this methyl right here is further downfield. It's at approximately, we'll call that 2 ppm. And it shows up as a singlet, 1 peak, and that makes sense again because if the carbonyl has 0 protons, then 0 plus 1 using the n+1 rule equals 1, so we'd only expect a singlet there. So with all of this evidence piled up, we can confirm the final structure of the compound being one of these butyl ketones, okay? So it would actually be 2-butanone is the official IUPAC name. And this is supported by all the spectroscopy here. So hopefully everybody found this useful. As usual, please remember to subscribe and hit the bell notification. We've got new courses coming out on HPLC training. If you would like, there are plenty more videos like this if you go through the playlist, and I'll be continuing to add them as I have time. So check those out if you need a lot of practice solving before an exam or something like that. Again, if you want to support the channel, in the link below, there is a link to chemcomplete.com where you can buy the guide. It is almost 40 pages. It has additional practice that you're not going to find here on the channel. And I walk through step by step and give you everything broken down, how you do degrees of unsaturation, how you analyze your mass spec. And we go into all the different regions for things like IR, all the different ppm shifts, and an understanding of how NMR works. So if you find that that might be useful, go ahead and check that out. And other than that, just make sure you hit the like button if this was useful to help boost the algorithms so I can continue to make content for you guys. And have a fantastic day. Feel free to leave comments if you have any questions, and I will see you in the next course.